Hello and welcome back to the course on artificial intelligence. Today we're talking about the temporal difference. Now, it's a very important tutorial because temporal difference is the heart and soul of the Q-learning algorithm. This is actually how everything we've learned so far comes together into play inside Q-learning. So let's have a look. Remember the time when we talked about deterministic versus non-deterministic search? And remember how we said, in this case, it's when the agent wants to go up, he definitely goes up. And when, in this case, he wants to go up, there's a 10% chance he'll go left, 10% chance he'll go right, and an 80% chance he'll go right, go straight up. Well, these numbers are, of course, arbitrary and can be different. And this whole concept is could be different in different problems. So it doesn't have to concern which way he's moving, just that there's some randomness, something that's out of the control of the agent happening inside this environment. And what effect that had is, as you remember, was that in the deterministic example, it was very easy to calculate the V values. Well, not necessarily always very easy, but in our case, we could just simply calculate them by using the Bellman equation, and we had the exact values. And then, as you remember, I very carefully mentioned that these values for the non-deterministic search example are off the top of my head. They're not calculated. At that time I said we're just not going to calculate them because it's very complex, but the computer could do it. And we just went along with these values that are just values that I made up, but they did get the job done. They helped us understand the concepts. Well, now we're going to return to that a little bit and understand what exactly is going on here. Why is it so much harder to calculate these values in the non-deterministic example? Or generally speaking, in these problems, in these environments and the agent going through them, why can it be so hard to calculate these values? Well, when you think about it, because when the agent moves, for instance, from here to the right, he doesn't necessarily always move that way. Sometimes there's a chance that he'll go when instead of going straight. So let's call these northeast, southwest. So instead of going west, the agent might sometimes go south. And for instance, from here, instead of going north, he might sometimes go east. So here, instead of going east, he might sometimes go south. And here, instead of going north, he might sometimes go east or west. And here, instead of going north, he might sometimes go east or west, and so on. And therefore, in order to calculate this value, you would need to know what this value is. But the interesting thing is that in order to calculate this value, you need to know what this value is. So there's a lot of recursion happening here, and therefore, you cannot just define what these values are. And on top of that, this recursion is not deterministic. It is sometimes it happens this way. Sometimes instead of going up, he'll go right. Sometimes instead of going up, he'll go left. Sometimes when he wants to go up, he will go up. So it is subject to chance. And so maybe many times the agent will go through this path and he'll go up, and he'll think that from here he always kind of goes up, and so the value of the state will be good. And then all of a sudden he'll drop into the pit and this value will go down. And so therefore you can see how there is some stochasticity or randomness to this whole calculation of these values because they're all interlinked. Plus on top, you've got that randomness that's inherent in the environment because there's a Markov decision process. So that's where all of this comes together, and that's where we're going to introduce the concept of the temporal difference, which will allow the agent to calculate these values. And here we were dealing with V values, and since then we've already moved on to Q values, so that's what we're going to be working with. We're going to be looking at Q values. So as you recall, this is our Bellman equation for Q values. So a Q value, or the value of performing a certain action A in state S, is equal to the reward that you get after performing that action, so immediately after performing that action, plus you get the maximum, you get the gamma of the sum of all the possible, so you kind of get the expected value of the state that you will end up in. So as you recall, that was our formula for the Bellman equation. And now, just for simplicity's sake, we're going to rewrite it in the old-fashioned way, in the way that we used to talk about the Bellman equation before we knew about the stochasticity. So, as you remember, this was our Bellman equation in the sense of a deterministic search example, because here you don't have that expected value. You don't have the sum across all probabilities. You just have that as if it's determined where you're going to end up, what state you're going to end up, and then you're taking the max in that one state. And the reason we're rewriting it is simply, the only reason is because it is just easier to write it, and it'll be easier to us to follow along with the formula. So we're going to just remember that we replaced this part with this part, and also you'll find this notation in a lot of literature, so it'll be easier for you to follow along with other sources if you're studying those. But do remember that, in fact, what we mean is this probabilistic approach here instead of this notation. It's just easier for us to operate this and understand what's going on, and just kind of like look at the equations so that they're not too cluttered. But once again, just remember that, in fact, what we mean is this probabilistic approach over here. And so we're actually nearly done, so let's have a look at what's going on. So here is our blank state of the maze. We don't have any Q values. Let's see, or we may, but let's just keep it blank for now. Let's just look at one of the states, or at one of the cells, this one specifically. And here we have, for instance, for the action of going up, we have a Q value that we've calculated. So it's not that we don't have any Q values yet. We do, but we're just not illustrating anything. We're just keeping it blank for simplicity's sake. But we have the agent's been walking around for some time, and let's say hypothetically somehow he's calculated this Q value of going up or north from this state, from this specific cell, and the value is Q, S, and A. And so now what we have, so he is currently where this blue arrow is pointing. The agent is sitting in this cell. And now he needs to make a choice. Where is he going to go? And he knows the value of the action going north, and that is Q, S, and A. And here I'm saying before. And the reason for that is because that is before he takes the action. He hasn't taken the action yet, so he's still in this cell. And before he's taken the action, the value here is Q and S and A. And now he actually takes the action. So let's say he decides this is the best one, he takes the action, and he moves up to this cell. Well, now what happens is, now comes after. So after he's taken action, we can measure what is this value. Let's just calculate this value. The value of the reward for taking that action plus gamma times the maximum of this new state that he's just gotten into, S prime. And so the maximum across all possible actions in S prime. And so what we have here is the value before of that action, and then we've calculated this metric afterwards. But as you can recall from the previous formula, so if we go back very quickly, from the previous formula, what we just calculated is indeed the value. That is how Q of S and A is calculated. So this right part, we've just calculated it separately, but after we've taken the action. So once again, before we knew a Q of an S and A value, something that we've calculated through our iterations previously. So a value that's stored in our memory, so just like a number that we know. And now, after the actions being performed, we know what reward he actually got, what reward the agent actually got, and we can calculate this new value. So in essence, we're kind of recalculating this value, but now with new information. The new information is the reward that we got. And plus what state we ended up in and what the maximum across that state, for what this new value is for that specific state that we're looking at. So what the value of that being in that state is. So basically the Q of an S and A, but given new information. And now the temporal difference is defined as TD of A and S of these two, of the difference between these two. So here, the first element is your after value. So the kind of like Q of S and A, but calculated afterwards. And the previous Q of an S and A, which you had stored in your memory. And so the question is, are they different? So ideally, they should be the same. Ideally, this should be the same as this, simply because this is the formula for calculating this. But the thing is that this is not something we calculate. This is something that we have from empirical evidence, something that we have from just going through the maze many times and calculating. So this is something we've come up with so far. It's not related to the current iteration. It's something that we came up with previously, not a long time ago, but in one of our previous iterations going through the maze. Whereas this is something we've calculated just now. And there is no guarantee that they're going to be the same. Because of the randomness that exists in the maze. Because this could have been calculated and some certain random events were triggered, and this can be calculated, different random events were triggered. And so now let's rewrite that over here. Let's just move it up there. So how do we use this? The question is, okay, so we have this temporal difference. How do we use this? And why is it called a temporal difference? Well, the reason it's called a temporal difference is because you're basically calculating the same thing. You're calculating Q of S and A. So the Q value of that action, you're calculating here and you're calculating it here. But the difference is time. This is your Q of S and A previously. This is your Q of S and A now, your new Q of S and A. And the question is, has there been a difference? Have there been a shift between them in time? And how can we use this to our advantage if there is indeed has been a shift in time? Well, one thing what we could do is we could say, okay, well, our Q of S and A this new value doesn't equal the old, so we're going to get rid of the old. We'll forget about the old, and we'll just use this as our new value. But that would not be smart. And the reason for that is that in our environment, random events can sometimes happen. And what if our old QS of S and A was something that, consistently happens like 80% of the time, and then like was represented by what happens 80% of the time, and then this new one just what happened due to randomness. In that case, we're going to throw away the one that is responsible for the bulk of the situation, and we're going to replace it with something that happens only 10 or 20% of the time. That wouldn't be the best approach to go. And that's exactly why we don't want to completely change our Q values. We want to change them step by step, a little bit by little bit. And that's why we're going to use this temporal difference in a specific way. So we're going to say, here's a formula. We're going to take our Q of S and A, and we're going to update it in such a way. We're going to take the old value of Q S and A, and we are going to add alpha times the temporal difference. So alpha is going to be our learning rate. That's a new parameter that we're introducing. That's how quickly is the algorithm learning. So basically, we're taking this difference, and whatever it is, we're adding it on to our previous Q of S and A. Now, this formula probably doesn't make any sense, or just by looking, it doesn't make any sense because you've got Q of S and A here and Q of S and A here. It's the same thing, so it probably should negate each other. But we're going to rewrite this in a bit of a different way. So I'm just going to show you again. So I'm just adding time to these formulas. So here is QT minus 1, the previous. Here's QT minus 1, the previous. Here's QT, the new. There should be a circle here, a red circle here as well, but never mind. And here we've got alpha temporal difference, the current temporal difference. So you can see what we're doing. We're saying, okay, let's take our current Q is going to be equal to our previous Q plus whatever temporal difference we found times alpha. This formula over here is the heart and soul of the Q learning algorithm. This is how the Q values are updated. And it's good that we've already learned what Q values are, what gamma is, what R is, and what all of this stuff is. And now all we need to see is that you have a previous Q value. Yes, that's good. And then what can happen is that when you actually do take the action, when the agent takes action, he'll get a reward and he'll end up in a state. And so based on that, he can calculate, okay, so what should have been the Q value of that move that I made? And now that is this part of the equation. Subtract the old Q value, gets you temporal difference. And now you need to take a alpha times temporal difference. And that's how you're going to adjust your Q value. That's what you're going to adjust your Q value by. And now just to finish off, this is kind of like, this is sufficient to understand what's going on. But just to clarify things even more, or perhaps maybe confuse things even more, what we're going to do is we're going to take this temporal difference, or this temporal difference over here, and we're going to plug it into this formula. So we're going to take all of this part and plug it into this formula and end up with a huge equation. So here we go. There's our equation. So this is the full equation with the temporal difference written out completely. And the reason I wrote this out is, well, first of all, you'll probably find this in other literature if you study it. And the second thing is that it makes some things a bit more complex. Yes, the formula is longer, but also makes some things a bit clearer. So for instance, you can see here the role alpha plays. You can see it better because look at this. Here you've got qt minus 1, and here you got qt minus 1 with a negative sign. So if you plug in alpha equals to 1, if you put a 1 in here, then this will negate with this. So they'll destroy each other. And all you'll have left is this part. And what that means is exactly that situation where we said, all right, so we've got a new value, which it should have been. Let's update our Q value with the new value and forget about whatever we had previously. And as we discussed, that's not the best approach because there are random events here and we want to update things step by step. And on the other hand, if you set alpha equal to 0, what happens then is that you completely forget about this whole part and your qt, the new one or the current one, is going to be always equal to the previous one. So you're not going to be learning anything. And that means whatever is happening in the maze doesn't matter because you've decided on your qt value a long time ago and you're just going to keep it. And so that's why alpha shouldn't be 0 or shouldn't be 1. It should be somewhere in between, and it's going to allow you to learn slowly, step by step. It's going to allow you to, the agent, as it goes through the maze, is going to get this temporal difference, and slowly and surely this value is going to get updated and updated and updated. And what will happen eventually is that at some point, hopefully, the algorithm will converge. And what that means is that this temporal difference will start becoming closer and closer to 0, and eventually will be just, well, very close to 0, or even 0, 0, 0, 0. And what that means is that every single time your new qt value, or your new calculated value, what it should have been, so not this one, but what it hypothetically should have been after you take the step, will be just equal to your previous qt value. And then it's 0, and that means when your temporal difference is 0, it means your algorithm has converged, and it's not really necessary to continue updating what's going on. It's not necessary to continue updating your Q values. The caveat here is that the only time, probably one of the only times when you would still want to continue performing this whole, updating of your Q values, if the environment is constantly changing. If not just, it's not that it just has some random stochastic events in it, but the environment itself is modifying, is morphing, is changing with time. So you continuously need to learn because it's not possible for you to learn everything and come up with the optimal policy because the optimal policy is also changing with the environment all the time. In that case, you will need to continue calculating temporal difference and calculating the Q values. But other than that, that's kind of like an extra complication. Other than that, this is how Q values are updated. So this is the main formula of the Q learning algorithm. And this is kind of like the expanded version of that. And now it should all come together and make sense why we have the Bellman equation and not only what it represents, the Q values, but also how the agent goes about updating its Q values and finding exactly what is going on in that environment so it can come up with the optimal policy. So I know this is quite a lot to take in, but hopefully you enjoyed today's tutorial and hopefully you were able to take away the underlying concepts and intuition behind Q values and what the whole notion of temporal difference is and why it's important, why it helps us slowly train our agents and get them to understand their environments that they're operating in. And if you'd like to learn a bit more about temporal differences, then a very popular paper is Learning to Predict by the Methods of Temporal Differences by Richard Sutton of 1988. We've already had a reference by Richard Sutton as well, but this is another one. And actually he has a book, so if you get into his writing style and his style of communication, then check out his book as well. It's kind of like a more expanded version of all of these things. I haven't read the book, but that's what I'm imagining. At the same time, this is the link to the paper, and you can learn a bit more about, or probably a lot more about temporal differences there. Now make sure to check out these videos on the right or the full course in the description to continue your learning, and I look forward to seeing you there.